Hey everybody, today we are going to be taking a look at a topic that you have seen before. For some of you, it was last year. Actually, for everyone, it was last year, but maybe it was 2 years ago also. In pre-calculus or in calculus AB, you studied something called optimization, which has problems that look like these. What is the minimum sum of two positive numbers with a certain product? Minimizing a sum. Find the dimensions of a triangle that maximize the area. Trying to create the maximum possible area. Maybe something like a farmer with a field and a certain amount of fence, and he wants to maximize the area of the enclosed region. Or maybe I'm manufacturing boxes or packaging and working for Amazon or something like that, and I want to create storage containers that have a certain volume but minimize the cost. And so we'll see a lot of different things like this. But the basic calculus idea goes like this. When we are looking at a function, whatever that function is, whether that function represents the area of a triangle or the cost of manufacturing boxes, we have some function. What it's going to boil down to, and probably the most difficult part of this, is to get something as a function of one variable. Now in Desmos or on your graphing calculators, you've got y as a function of x. But if I've got a graph that looks something like this and I want to find where the maximum value is, well, here we go. I've got my equation for this function. And if I then find what the derivative looks like, I can say that that derivative will be equal to 0 at a spot that corresponds with that maximum. So find the equation for the function, take the derivative, set it equal to 0, solve for that value. You've got yourself the x value. That's your maximum. Maybe that's the length of a side of a triangle. Maybe it's the length of a side of a field. Or maybe we've got a graph that looks more like this, where I've got some kind of a, who knows what kind of a cost function or something like that. I want to minimize this. I want to find that minimum point. Well, same idea. All we have to do is figure out what the derivative looks like, and the derivative will again have a 0. Find the derivative, set it equal to 0. That 0 of the graph of the derivative corresponds to a minimum of our function. But again, we need to have cost, area, volume, size, whatever we're talking about, whatever we're trying to maximize or minimize, as a function of one variable. This is how we're going to. These are my step-by-step, tried and true method for figuring out how to find these things. Now, most of these steps, actually I take it back, half of these steps are the same as what they were in pre-calculus. And so this is going to look familiar. When we're doing these farmers building fences problems, you have seen these problems before. So the first 3 steps you've done. Find an equation for the quantity that you're trying to maximize or minimize. And by the way, you should probably pause the video at some point and make sure you get these 6 steps down in your notebook. But I'll go ahead and describe them, and then we'll go through a few examples before I am done with this video. An equation for the quantity you're trying to maximize or minimize. And this is big. I'm tutoring a young lady who's taking a pre-calc class in another school district, and I emphasize this so much with her, that if I'm trying to maximize the cost, create a cost function. If I want to maximize the profit, then I want a profit function. But you want whatever you're trying to maximize or minimize. Optimization means one or the other. I'm trying to maximize or minimize something. So find an equation for that quantity, whatever it is. Now you may have more than one variable. You may have something like cost as a function of time and quantity of something that you're buying, or whatever it is. You may have more than one variable. And if that's the case, then we need step 2 that says if you have both time and quantity, then you need something that ties those 2 things together, time and quantity, so that you can do what I'm saying in number 3. If I say time is equal to the square of the quantity, and I'm making this up, this doesn't make any sense, but if I've got an equation that says something like that, I can then take that variable and plug it in place of time, thus giving me a single variable equation. And again, we'll go through, I'll show you some specific examples before we're done. At that point, when you have cost as a function of one variable, in pre-calculus, you went to the calculator and you looked at the graph and you said, hey, calculator, where is the maximum? In calculus, we're going to have to do this without using a calculator for the most part. We're going to use calculus instead, which means take the derivative. A maximum or a minimum point on whatever graph we're looking at will correspond to a 0 of the derivative. So you take the derivative, set that equal to 0, and solve for those values. Now, this is going to be easier said than done in some cases. Sometimes it will be extremely difficult. In some cases, we may just have to go to technology and use the technology to find it. And I realize this is a little bit of a contradiction because I want to do this without a calculator. I want to do it without letting my calculator say, here's the maximum point. But I am allowed to use my calculator to find zeros. And that's something that we'll be talking about as we get closer to the AP test, where finding zeros of a function is one of the things that is allowed, one of the 3 things that we're allowed to do on a calculator. But more on that later. Finally, my last step is the one that we won't spend that much time dealing with, but it's something that we should always have in the back of our minds, because if I have only found where the derivative is equal to 0, and that's all that I've thought about, it's very possible that instead of maximizing something, I am minimizing something. And if I'm working for Amazon and instead of minimizing the cost of producing packages, I have maximized the cost of producing packages, I just lost my job because that is a fireable offense. But anyway, there we go. So those are the steps. Go ahead and get these copied down. We'll refer back to these as we're going through the problems. But I think now is a good time for us to take a look at some problems. All right, well, we're going to start with a relatively simple one. And when I say relatively simple, part of what I mean by that is if I ask this question, give you a second to digest this, what is the minimum sum of 2 positive numbers with a product of 72? It's guessable. If you think about this, if I were to be quiet for a moment, or if you were to pause the video for a moment and think about it, you might be able to just guess what those numbers are. And actually, when I introduce the idea of optimization to my pre-calc students, I might use a number like 72 with a lot of factors and just ask, what are 2 numbers that I can multiply to get 72? Well, 1 and 72 is 72. Their sum is 73. 12 and 6. Yeah, 12 and 6 works. And 12 plus 6 is a lot less than what 72 plus 1 was. We're getting closer. We could play around with a little bit and start to notice what happens when the numbers are far apart versus close together. But ultimately, to do this using calculus and to know that we have the right answer instead of thinking we might have the right answer, is to follow the steps. Number 1 says, find an equation for the quantity I'm trying to maximize or minimize. In this case, I'm looking for a minimum sum. And so I'm going to use S to stand for the sum, because that's what I'm trying to minimize. And the sum of my 2 numbers is x plus y. X will be one number, y will be the other. Now, this is a simple equation, but it's too complicated because it's got too many variables. I want the sum in terms of one variable, and I've got the sum in terms of 2 variables. So I'll have to use more information. Also, I'm going to have to use the fact that the product of those 2 numbers is 72. Step 2 says find equations that relate the variables that affect the value of the quantity, in this case, the sum. And so the relationship between x and y is that x times y is 72. So then step 3, substitute the equation from this step into that step, solve for x, solve for y. It doesn't really matter which one we do, so I will say y equals 72 over x. And now I've got something that I can plug into this equation in place of y. Sum equals x plus 72 over x. And now the graph of this function is actually pretty similar to the second graph that I showed you on Desmos just a moment ago. If I graphed it, we would see, let's see, I'll put it right here. We would have a graph that would look something like this, where there's some minimum value. That minimum value is going to occur when the derivative of this function is equal to 0. So step 4, take the derivative. Let's see, the derivative of 72 over x, that's the same thing as 72x to the negative 1. So the derivative would be negative 72x to the negative 2. So something like that. And where the value of this function is 0, that's where my optimal solution is going to be. So I'll go ahead and set that equal to 0. 1 minus 72 over x squared equals 0. Not uncommon to have a positive and a negative term, so I can subtract 1 over to the other side. 1 equals 72 over x squared, which means 72 equals x squared, which means, and I'm going all over the place here, x is positive or negative square root of 72. Whoops, sorry about that. I'm going to throw the negative 1 out because I'm only allowing positive numbers. If I don't require that they both be positive, I suppose I would have to consider negative, but in this case, I'm going to say that x is the square root of 72. And then to find the value of y, I could take 72 divided by the square root of 72. If you do that, you'll find that y is also the square root of 72, which makes sense. And then we should probably answer the question, what is the minimum sum of these two positive numbers? Well, it looks like x plus y in this case. My minimum sum is the square root of 72 plus the square root of 72, 2 times the square root of 72, and I could simplify that. Let's see, I could take a 36, the square root of 36 out of there, and get 12 times the square root of 2. Now in pre-calculus, when we're just taking guesses at it, we might get to 8 times 9 as a way to get 72, and 8 times 9, 72. 8 plus 9 is only 17. That's probably the smallest one we get. And then a lot of times in a class like that, I'll have a student who kind of sees what's going on, and they'll say, well, what about the square root of 72? And then we would use a calculator and try to figure out what that is approximately, but that is the exact answer that we're looking for. So there we go. Start with this equation. This is my main equation. Use another equation to find a variable to plug in. Take that new equation, differentiate, find where that derivative is equal to 0, and then depends what our question is. Okay, let's try another one. Probably won't do all of these. Let's see. We minimized that one. Let's maybe do this triangle one here. I want to find the dimensions of the triangle that will maximize the area. So it looks like my hypotenuse is fixed at 10. I have a right triangle, and that's a big clue. Triangles make for good optimization problems because we can do a lot of stuff with triangles. We can use areas of triangles. We can do perimeters of triangles. We can do Pythagorean theorem. We can do trigonometry, all kinds of good stuff we can do. But in this case, I'm trying to maximize the area. So my main equation will be the area of this triangle. And there's a few different area formulas I could use, but 1/2 base times height is probably the way to go on this one. X times y. You can't quite see that, can you? There we go. If only this were live, you guys could chat and let me know when I push it off the screen. I'll try to keep track of that. I've got too many variables. I've got area in terms of x and y, so I need some other equation that ties x and y together. And if we were in class, I would pause and someone would say, well, Mr. Crow, what about the Pythagorean theorem that says x squared plus y squared equals the hypotenuse squared? Wonderful. I'll solve this equation for y in terms of x or x in terms of y. Either way, it's not going to matter which one we do. I'm going to solve this for y in terms of x. Here again, technically, I should probably consider both the positive and negative square root, but then I realize I'm using lengths, and both of these quantities are going to be a positive quantity. So I'll only deal with the positive square root of 100 minus x squared, and then I'll plug that into my area equation. This gives me area equals 1/2 x times the square root of 100 minus x squared, which is area as a function of x. Sweet. So whatever the value of x is going to be that will maximize or minimize, which let's talk about that. If I want to minimize the area of this triangle, I suppose I could let x be really close to 10, so it's a very flat triangle. In fact, I suppose if x was equal to 10, it ceases to be a triangle at all and becomes just a line segment. Or I could let x get to be really large, very small, infinitesimally small, so that the height of the triangle is about 10, and then we've got kind of our endpoints of the scenario. If I find something in between -10 and 10, let's go between 0 and 10, I'm going to feel pretty good about that solution. But let's actually try to find it. In pre-calculus, you would have gone to the calculator and said, hey, calculator, what is the value of x? Graph it, find the value. In calculus, we're going to differentiate the derivative of this function. We got product rule. I've got 1/2 x out here and the square root of 100 minus x squared. So I am going to do the derivative of 1/2 x times the square root of 100 minus x squared. Derivative of the first times the second plus the first times the derivative of the second. The derivative of something to the 1/2 power is something, 1/2 times the something to the -1/2 power times the derivative of the stuff inside. Derivative of the stuff inside is -2x. Now, on the gateway quiz for this topic, I said don't simplify, just leave it as it is. And I probably said something like, at some point, we're going to need to try to solve and find where this is equal to certain values. Well, here we are. That's what we're going to have to do at this point. I want to find out when this is equal to 0. So let's simplify. Let's see what we can do to get this simplified. Not much I can do with this first part. I guess I can write it as a fraction, the square root of 100 minus x squared over 2. And then the second stuff, well, I see a 2 and a 1/2 and another 1/2. So at least one of those 1/2s is canceled out by the 2. I've got a negative. Everything else is positive here, so I can make that minus. There's the 2 from one of the 1/2s. The other one's going to cancel out. I've got x times x. Let's see, 1/2 and a half and a 2. That's taken care of with the 2 in the denominator. X times x, the negative. All I have left is this stuff to the -1/2 power. So let's make that a radical in the denominator. Ooh, my stomach just growled. I hope you didn't hear that. Also, my wife is practicing cello upstairs, so if you hear a mysterious noise, that is what's going on. Anyway, here we go. Now I have to try to solve this. I am going to run out of paper. I'll just have to add on to this. How do we solve something like this? Well, take a look. I've got something minus something equals 0. So let's take this term. Let's add that over to the other side. See what that looks like. Keep this, the square root of 100 minus x squared over 2 would be equal to x squared over 2 times the radical. This fraction equals that fraction. Let's cross multiply. Multiply these two together, multiply those two together. How convenient that the square root of 100 minus x squared is being multiplied by itself. I remember thinking that my calculus teacher was so smart that he came up with these problems that worked out so conveniently. And then I found out when I wrote my own problems that it just kind of happens. Not to say that my calculus teacher was not smart,
He was actually kind of a jerk, but I loved him. He was a really, really good guy. Mr. Ozzie was his name, and he passed away a few years ago, and I was very saddened to hear that. Anyway, here we go. 2 times 100 minus x squared equals 2 times x squared. And that's not going to be too bad to solve. I'm looking at the video. Hopefully, I'm writing on the back side of the sheet I just wrote on, but looks like you should be okay. Let's solve this. Let's solve for x. I've got 200 minus 2x squared equals 2x squared. I'll add 2x squared to both sides. Divide both sides by 4 to get x squared equals 50. So here again, I'll ignore the negative value and say that the square root of 50 is the only one that makes sense. Again, I knew it would have to be somewhere between 0 and 10 because those would be the values where I have either an unreasonably narrow or unreasonably flat triangle. And so since the square root of 50 is somewhere between 0 and 10, I feel pretty confident that it is a maximum area. I could do the second derivative test to make sure of that, or I could look at what the value of the derivative when x is less than the square root of 50 or greater than the square root of 50 to verify that the derivative is, let's see, positive to the left and negative to the right. A lot of different ways to think about that, but the important thing here is that I've got an answer. I feel good that this is the x value that corresponds to a maximum, and so there we go. Let's do one more. I think I'm going to avoid the ostriches. I feel like you did these problems to death in pre-calculus. We can maybe take a look at one once we're back to synchronous on Thursday. I think I want to take a look at something like this one. We'll finish with this. We're already at about, we got a long video already, but that's okay. This is standing in for a lesson on both Monday and Wednesday. Find the minimum cost of a rectangular storage container with the following properties. Volume is 100 cubic feet. The length of the base is half of the width. That should look familiar from pre-calculus. And then the top has this cost. The reason I like this problem is because it gives us the chance to talk about the difference between minimizing the surface area versus minimizing the cost. If the cost is uniform, if I don't put step 3 up here and I just say we're using cardboard or aluminum or titanium or whatever we're using to make this storage container, if everything costs the same, this is a surface area problem. Minimizing the surface area will be minimizing the cost. But because the top costs more, we're probably going to end up with a container that's a little bit taller and a little bit more narrow, cutting a little bit of that cost from the top without losing too much of the volume. And the case that I often will use is, imagine if I wanted to make a can of Coca-Cola, except I'm going to use solid gold diamond crusted material for the top, and then everything else is cheap aluminum. And I want you to think about what kind of a Coke can that still holds a full can of Coke. It still needs to hold whatever it is, 12 fluid ounces. But again, the top is going to be made with solid gold diamond crusted material, and the rest is just cheap aluminum. And the image I have is something like this, where I've got a very, very tall, skinny can of Coke, because I want to make that, I want to make that top relatively small. It's the pixie sticks of Coca-Cola. Now, this is less extreme than that, but it does kind of illustrate what's going on. Now, I'm going to spoil the end of this problem and just show you, if we were to minimize the surface area and do this exact same problem with the exact same criterion, I've got the set volume, the base is half of the width. These are the dimensions that we would get. If I minimize the cost, which we're about to do in just a moment, you see that it's not a huge difference. because the difference in cost between the top and the rest of it wasn't gigantic, but it was enough that there is a noticeable difference between the dimensions that I find if I minimize the surface area and if I minimize the cost. And in fact, if you're bored, try both of these problems. We'll do the cost equation or the cost situation, and the surface area one's actually even more simple than what we have. So we can maybe talk about that a little bit. But let's actually do this problem. Man, I got paper all over the place. Volume is 100 cubic feet. So I'm going to get a plain sheet of paper here, so it doesn't have writing on the back of it. That'll make for a better video for you guys. So I am going to imagine this storage container, something like that, with height and width and length. And my volume is 100 cubic feet. The length of the base is half of the width. That's one of the things that I'm given in the statement of the problem. So the length is half of the width, or maybe the width is twice the length, I suppose we could say. The top is $3 per square foot, and everything else is $2 per square foot. So I'm just writing down information, but one of the pieces of information that I have not written down is the most important piece of information, and that is I'm doing a optimization problem where I'm trying to minimize that cost. I need a cost equation. This will ultimately be the equation that I differentiate. All the rest of this stuff is just going to go into this and help me figure things out. All right. So my cost equation, I have to factor this in. The area of the top, well, that's just going to be width times the length times that $3 per square foot. Whatever this area is multiplied by the cost per square foot. We've got that, plus the bottom, width times length, area of the base, times $2 per square foot for that part. So that's top, that's the bottom. The left side and the right side are both going to be the same. The left side and the right side are both L times H. So I've got one on the left, one on the right, L times H. Times 2, because I've got 2 of them, and then times 2 for the amount per square foot. So again, the first 2 comes from the fact that I've got both the left and the right side. And then the second 2 comes from the cost of the left and the right side. And then finally, we've got the front and the back. The front is W times H, and so is the back. Same thing. So W times H times 2, because I've got 2 of them, and then times $2 per square foot. So this is the front and the back. I've got width and length and height. So I've got all 3 of these things. But I've also got information that I haven't used yet. The volume is 100 cubic feet. The volume of this box is width times length times height. There's one equation tying these variables together. The length is half of the width, or maybe I'll say the width is twice the length. That lets me replace all of the L's in my equation with either 1/2 W's or replace all the W's with 2 L's. That's good. That's good. I've got a lot of variables. The fact that I've got a lot of equations over here is helpful. Now, tempting to replace the W with 2 L's right away, and I'm not going to say you can't do that, but I'm going to start with the equation for volume first. I'm going to get rid of one of the variables, and then whichever variable I get rid of, I'm going to use that to figure out which other variable I should get rid of. So I'm actually going to take this equation and say if the volume 100 is length times width times height, that means, and frankly, I'm going to be a little bit lazy here, and I am going to get rid of, let's see. Well, I'm going to be a little bit clever about this and say the height in terms of the other two variables, if I can get rid of the h, I'll be able to use these equations to get rid of either w or l. So if I say height equals 100 over WL, I can replace all of my h's first with this, and then I can replace all my w's with 2l's, and I'll be down to a single equation in terms of just the length of, I guess, the length of the side of the box. And so actually doing that process, my cost equation, after doing this replacement first, I've got 3WL plus 2WL. So far I'm not doing anything. Plus I've got 4LH. So I'm going to say 4L. And then here I'll replace that H with 100 over WL. And those L's will cancel out. That 4 times 100 will become 400. I'll do that next. And then here I've got, again, 4W times H. And I'll replace that H with 100 over WL. And again, those W's will cancel out. In fact, I might as well do that. I've got 3WL and 2WL. Let's go ahead and call that 5WL. I'll combine the 4 and the 100, cancel out the L's. I'll be left with 400 over W. And then 4 times 100, cancel out the W's to be left with 400 over L. Sweet, that takes care of that substitution. I'm down to cost in terms of two variables. And because I was a little bit strategic about this, I can get rid of the W by replacing it with 2L, or the L replacing it with the half W. I think I'd rather not have to plug a half W into the denominator of this one. I think I'm going to use this W equals 2L and plug that in place of all of my W's. So my new cost equation will be 5 times, replace that W with a 2L times L. I've got 400 over W, which is replaced by 2L, and 400 over L. I'll just keep as is. And check it out. I've got cost as a function of one variable. I'm going to simplify this a little bit. Let's call this 10L squared. And then I've got a little bit simplified. This is 200 over L plus 400 over L. Let's combine these two terms. Again, 200 over L plus 400 over L gives me 600 over L. And that's not all that bad. Finally, we can do some calculus. If this is my cost equation, then C prime is just the derivative of this, 20L. This looks familiar, 600 over L, that's 600L to the negative 1, so its derivative is negative 600L to the negative 2, which I will write like that. And there we go, I've got my derivative. So let's go ahead and set this derivative equal to 0. If 20L minus 600 over L squared equals 0, here we are again. Positive term minus another term equals 0. Let's move that term over to the other side. I'm going to multiply by L squared, divide by 20 to get L cubed equals 600 divided by 20. I believe that's 30. And the length of one of the sides is the cube root of 30. And then once again, I should be considering my step 6, which is, did I just find a maximum or did I find a minimum? But if we think about this situation, if I've got a rectangular storage container, obviously L going to 0 results in a really tall, skinny box that if it's got a set volume, it's going to have an incredible height that would give me a large surface area, hence a large cost. And if L gets to be really, really, really big, then this gets to be really, really flat. And we've got the other extreme case where I would have a whole bunch of packaging on the top and the bottom, and then our cost is going to go out of control. I'm using logic to think about this. Maybe I should be using calculus and taking the second derivative. And in fact, this would maybe be a good application. The second derivative test applied here is not going to be too bad. If I take, oh, why not? Let's just go ahead and do this. The second derivative would be 20. Let's see, this is minus 600L to the negative 2. So it'll be plus 1200 L to the negative 3. And so now I've just got positive quantities. If I plug my solution, the cube root of 30, in here, I'm not going to think really hard about this because this is going to be positive. And if my first derivative is 0, my second derivative is positive, we have a minimum. We definitely have a minimum to our cost. Find the minimum cost. I suppose if I want to find that minimum cost, I would plug it in here to find the minimum cost. I mean, I've got my answer. This is the length that will minimize that cost. I have cost in terms of that length, so I could plug it in here and find what the cost is. This video is getting to be long enough as it is, so I'll leave that to you. If you wanted to actually find that cost, we could plug that in. If I say find the dimensions of the box that minimize the cost, well, I just found the length. I know that the width is twice as long as that length. And then I also know that my height is the volume 100 divided by the product of the width and the length. And so I could find all of these things if that's what I wanted to find. So what we do at this point depends on what the question is asking, what are the dimensions of the container, what is the minimum cost, what is the minimum height, whatever it is asking. Okay, I need to stop at this point so this video doesn't get prohibitively long. Please take a look at the examples that are in the book. The book does a really good job of going through lots of different possibilities. Try the assignment before I see you on Thursday so we can wrap up optimization and talk about the rest of this chapter. Thanks for watching. My next list of things to do is to get to work on grading the quiz that you guys took. It is Wednesday night at 7 o'clock, and maybe I'll be able to get done with that. But good luck with these optimization problems. Give them a try. This is not something that's going to take like 10 minutes to figure out. Look at my examples. Look at the examples in the back or in the book. And well, I'll just have to take questions on Thursday. So good luck with this. I will see you. Have a good night, a good day. Depends what time it is when you're watching this. See ya.